Okay, this is for the higher level section. I'm going to put it on both, but if you want to watch it. Um, so, sorry about that. Okay, the next thing we're going to work on for the higher level, you have to know how to, basically sketch rational functions when there's a quadratic and a linear in the numerator and the denominator. So, let's see, rational functions. Continued. What I want you to do first is I want you to do y equals a plus b over ax plus b over cx squared plus dx plus e. Stick that in decimals, fool around with the sliders, and get a sense of what any of these graphs look like. What you're going to notice here is because there's a quadratic in the denominator, there's going to be two asymptotes. And because the quadratic is clearly getting to infinity faster than the numerator, this fraction is never getting to zero. I mean, it may start at zero, but as it gets really large, because the denominator is so much larger than the numerator, the vertical asymptote in all cases is going to be zero. Okay, so let's come back and let's take a look at some examples. Let's start with something basic. Once again, you've explored this, so you know what's coming. Let's explore this. Y equals 1 over x squared minus 4. Okay, so we know there's the asymptote. So x equals plus or minus 2 are the vertical asymptotes. We know because the denominator, the order is greater than the numerator. This is saying at 1, but this is going to take million, billion. So 1 over that is 0. So y equals 0 is a horizontal asymptote. Are there any zeros? Well, it's not getting to 0 because we know that at infinity, it's not getting to 0. And this is always 1. Let's deal with that in a second. Anyway, are there any y-intercepts? So x equals 0. Y equals negative 1/4. That's a y-intercept. Okay, let's sketch this thing. But once again, we're sketching based on previous knowledge. So we are putting up our axes on our paper. We are putting in our vertical asymptotes. Once again, pencil. In part 2, you can use a calculator. Any graph question, you can use a pencil. Let's see, x equals negative 2, x equals 2. Okay, I also know for this fraction, it's never getting to 0. Adding the infinities. So y equals 0 is also an asymptote. It's a horizontal asymptote. I also know that negative 1/4 is a y-intercept. Now the question is, I know that there's branches and maybe there's a weird thing that goes through here, or maybe it looks like a parabola, or there's a branch down here on this side. I don't know what to do. I kind of know what it looks like. So what I'm going to do is I'm going to make a sign chart. I'm going to see if there's positives or negatives at the important points. So in my sign chart, make a sign chart to determine if the function is greater than 0 or less than 0. So my important points right now are the vertical asymptotes. Let's see what's happening between all of them. So let's take a point to the left of negative 2. For example, negative 10. Well, negative 10 squared minus 4 is positive. Positive over positive, positive. I'll use different colors, actually, to make it fun. Let's see, I have blue, I have red, and I have pink. So, we'll start with black. Because it's positive, I know this part looks like this. It is asymptotic to 0, but it's above the asymptote. What's going on from 2? What's going on between negative 2 and positive 2? Well, every point here is negative. For example, like 1, -1. All this is negative. Now, we know from our experience in Desmos that we're going to have something that looks like this. It's asymptotic to -2 on the right. It's asymptotic to x equals 2 on the left. And it passes through this point. It might be a minimum. It might not be. If you have your calculator, you can check that out. But this is the general shape of it. Now, what's going on to the right? Let's use blue. Let's pick a point to the right of 2. I want to know if it's above or below. Because I know it's going to be like one of these branches. Oh, well, let's pick any point. Let's pick 8. Well, 8 squared minus 4 is positive. 1 over positive is positive. And therefore, I know it looks something like this. And that's the idea. We saw this in Desmos. That's what's going on here. Next example. Let's see. 3. Y equals 2x plus 1 over x squared plus 9. So now we're going to put a linear over this. And this is where we're going to talk about asymptotes and zeros. I'm erasing this because I need the space. Let's start over again. What did I say the example was? I said the problem was y equals 2x plus 1. Y equals 2x plus 1 over x squared minus 9. Now, you look at that and you're like, okay, that's fine. Let's break it down. Well, I know that x equals plus or minus 3. They're vertical asymptotes. I know that y equals 0 is a horizontal asymptote. Once again, this quadratic is getting much larger than that linear, which means this fraction is going to 0. It might come from the bottom or the top, but either way, at the infinities, the function is approaching 0. It's getting smaller and smaller. Once again, this is just x. This is x squared. The one in the line, 9, who cares? It's the x versus the x squared. That denominator is winning the race. Okay, are there any asymptotes? Well, I know that if x equals 0, then y equals -1, 9. So this is the y-intercept. And now I have a denominator. So I have a 0. 2x plus 1 equals 0. X equals -1/2. That's an x-intercept. That's an x-intercept. So you say to me, Mr. Adler, how is that possible? Because you just said that y equals 0 is a horizontal asymptote. And asymptotes are lines and the functions never touch them. Well, that's by the infinities. That's when you after you get out of this stuff, the halves, the ninths, the threes, once you start getting out 10, a million, then that's where the asymptote begins. But the curve could cross an asymptote early on. So don't think about it like that. So I think we have enough information to start to create our curve. Once again, we draw our axis. We plot our asymptotes in pencil. Am I recording? Yeah, sorry, this is a long video. I'm going to put in my new horizontal asymptotes. You have to write this in. Y equals 0, x equals 3, x equals -3. This is how you get the points in IB. You have to label these diagrams like this. Next, let's throw in some intercepts. Let's see. My y-intercept is -1/9. And my x-intercept is -1/2. What's going on here? This looks a little weird. But once again, we kind of know from Desmos, it's probably going to be that weird thing with a bunch of branches. So let's figure out from the sign chart what's going on. in the sign chart, like label, I can't think of the word, label your horizontal asymptotes and your zeros. Zeros, x-intercept, it's a fancy word for, it's a zero because we set the equation equal to 0. It's also known as the x-intercept. It's also known as the roots. They're kind of interchangeable, but they have specific meaning. Anyway, so let's take a look at this. So -3 and 3 are kind of important, right? But -1/2 is also important. We have to take a look at what's going on there because we can see the curve passes from above and below, or at the x-intercept, it's negative to positive. Let's plug in some values. Well, the first thing I'm going to tell you to do is leave this factor. It might help, it might not. It could help you or not. Let's have -5. I plug -5 because it's to the left of 3. I'm going to plug this in. I have negative, 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 negative. Right? Is that clear? Once again, I plug -5 in here. Yeah. No, that's not right. Yeah, no. Negative, negative, or negative, positive. So maybe I shouldn't have factored it. Anyway, let's pick something between -3 and 1/2. Right? What's a good number between -3 and -1/2? Let's choose -1. Let's choose -1. So let's see. 2 times -1 is +1 is -1. So that's negative. And -1 squared, 1 minus 9, that's also negative, which means this is positive. So, you know what, let me use the colors. This is going to be red. So we saw that when we plugged in -5, it was negative. When we plug in the value between -3.5, the curve is positive, and it looks something like this. What's going on between -1/2 and 3? Well, the best value is 0, and we already know from our asymptote that between -1 and 3, this curve is underneath the axis, or negative, right? If you plug 0 in there, you get -1/9. So it looks something like this. It passes through 1/9, and then it's asymptotic to x equals 3. Please remember, we know this from Desmos. What's the last thing we have to work on? Well, I want to know what's going on when x is greater than 3. Well, if I plug x is greater than 3, positive, how about like 10? So 2 times 10 is 21. 100 minus 9, positive. Positive over positive, positive, and I know from Desmos, kind of looks something like this. And this is how we graph a rational function where we have a linear divided by a quadratic. Find the vertical asymptotes. The horizontal asymptote is always 0. Get your y-intercept, your x-intercept. Start to make the graph. Make a sign chart. On this chart, you're going to label the asymptotes and the zeros, because that's where the action changes from above or below. And then substitute values in and see what the curve looks like. Now, we're not done. You did that last year, but Higher IB has thrown in something new and fun. You'll like this one. In this case, in the third case that you have to know, I'm going to erase this. Let's see, 5. Yes, I'm going to keep that. No, well, you know what? No, there's no point. Okay. So the last case we spoke about is now a quadratic divided by a linear. The next case is a quadratic divided by a linear. So what I want you to do now is I want you to flip that original one, and I want you to ax squared plus bx plus c over dx plus e. And I want you to just kind of like get a sense of like what's going on here. So take a minute, fool around with Desmos so you kind of know what you're looking for. And so you're looking at a graph. Okay, so we're back. Sorry, you're back, and you're looking at this, and something weird happens. Kind of you might get a graph that kind of looks like, it kind of looks like this, and you might say to yourself, you know what? It looks like there's an asymptote. Like maybe you turn your computer like sideways, and you go, you know what? It looks like there's an asymptote in here. It looks like there's an asymptote in here. And you're like, that's kind of weird, right? Well, that's the point of the medium. This is known as an oblique. Because it's turned. And the idea is, when you have a quadratic divided by a linear, you still get the same you still get the same rational function look, but now it's asymptotic to something that's called an oblique axis. So how do we find this out? Well, let's start with, let's see, number 5. Where's number 6? Okay, ready? Oh no, wait. Good. Okay, x squared plus 4x divided by 21 plus x plus 5. Now, you see, this was just one thing you saw. This is the one we're going to be seeing. So let's take a look at this. Sorry. This is 6. Okay. Move it over. Okay. No red hat. Sorry about that. We have y equals x squared plus 4x minus 21 over x plus 5. Take a look at this in Desmos so you kind of know what we're expecting. You'll be able to do this on your own. You're going to be asked to do this. What's going on here? Well, the first thing I notice is that x equals negative 5 is a vertical asymptote. Right? What else? You know what? I'm going to... That's fine. What else? I know that I can set the numerator equal to 0. So it's x plus 7, x minus 3 equals 0. Just skip to the next step. X equals negative 7, and 3 are zeros. Okay, that's fine. When x is 0, y equals negative 21 over 5. That's negative 4.2. So these are my x-intercepts. And this is my y-intercept. Okay. So the question is, if you put this in Desmos, actually, I was kind of exploring this. If you put that in Desmos, also put the line in y equals x in there. And you might say, oh, it's kind of close, but you know it's not the asymptote. The question is, what exactly is that line that this curve seems to be like getting really close to? Well, we have to do a little old school. Division. We can do. So I taught this last year, and I said use synthetic division. So let's do synthetic division first. So we're going to divide x plus 5 into the quadratic. Fine. So I know that So to find the oblique asymptote, divide x plus 5 into x squared plus 4x minus 21. Fine. We know x plus 5 equals 0. X equals negative 5. Stick that in the perch. Right? So we have 1, 4, negative 21. I took that from there. Right? I have 1, -5, -1. This is 5, and this is 16. It turns out, this is kind of cool. Kind of cool. It turns out that we can rewrite this therefore as 6. So if you think about it, this is the remainder. When you were in like 3rd grade, what did you do? The remainder, you put it over the divisor. So this actually is equal to, -16 over x plus 5 plus x minus 1. Okay? This is kind of cool. So it turns out this is cool. This is the vertical asymptote. This is the oblique asymptote, and it's -15 over x minus 5, but like twisted or rotated so that this is the new asymptote. Okay? Let's get a picture. So, here's our axis. We know that x equals -5. Is the horizontal, is the vertical asymptote. We know that y equals, and so y equals x minus 1 is the oblique axis. And so this is kind of cool. This function that we did in the beginning of the last video fits in here. So we'll do 1 or 2 more examples. Let's put some points in. We know that we have -7. We have 3. Right, because this is 1 and 1. And we have the y-intercept. What's the y-intercept? -4.2. And so you can kind of see, we know what this looks like. You have this in your notes from the first problem. I did this specifically, but once again, it's just going to be twisted. And now we have enough points. So it would look something like this. And that is how we graph a quadratic over a linear. Now, 7. Okay, we have to talk about something because I just learned something really important. It turns out that in the books have you do old school division. And so the question is, why do you have to do old school division? Why can't you use synthetic division? And the idea I just discovered, you cannot use synthetic division if the divisor is like 2x plus 5. Let's try another. So what I wanted to do was give you a problem that looked like this, like y equals, x squared minus 4 divided by 2x plus 1. If you do synthetic division with this, like so for example, I taught you set it equal to 0, and then x equals -1/2, put that in the perch, and do 1, 0, -4. This won't work. You can't do this with synthetic division. The only way you can do synthetic division is if the divisor has 1 as the lead coefficient. I didn't know that until yesterday. So I'm not going to give you 1. So we're going to have to do, so I can't give you that problem, but we can do another one. And the example I want to do, sorry about that. The last problem I want to do is x squared minus 16. X squared minus 16 divided by x minus 2. We'll keep it simple. Okay, same idea. Sorry, let me erase this. let's take a look at this. Something I didn't talk about. The numerator is greater than the denominator. Now, what does that say about our function? It means it's going off to the infinities, right? If you think about it, this is getting much larger than the denominator. So in our previous graph, we can see that clearly here that the functions go off to the infinities, and they go down to negative infinity and positive infinity. We're going to see the same thing when we have a quadratic divided by a linear. Right? Okay. Let's take a look at this. Obviously, you can look at this in decimals. You know what this is going to look like. So let's describe some things. So we know that x equals 2 is a vertical asymptote. We know, because we're experienced math students, there is no horizontal asymptote. Okay? We're going to get to that. But we know there's a slant. Let's see. We know that x equals plus or minus 4 are zeros. We know that y equals 8 is a y-intercept. The question is, where's our other asymptote? Well, you can do synthetic division. Bring on 1, 2, 2, 4, negative 12. So you have, so this function is y equals negative 12 over x minus 2 plus x plus 2. So this is the rational function. Kind of shifted about this, and this is the oblique. Or you can go old school. If you want to do old school, that's fine with me. Let's do old school together. X minus 2 into x squared minus 0x minus 16. I'll go old school if you want. This is x squared minus 2x, subtract the 2, 2x minus 16, plus 2, 2x minus 4, subtract the 2, 2x minus 2x is 0, negative 16 minus negative 4 is negative 12, and so you can see here, like the way you did it when you were kids, it's x plus 2 minus, 12 over x minus 2. It's the same thing. You can see it's the same thing. Let's get a sketch. Let's get a sketch, and then we're done. Let's see. We have our axis. We know that x equals 2 is a vertical asymptote. We also know that x plus 2 is another asymptote. You absolutely have to know how to graph this line this quickly. No exceptions. And you have to label it. X equals 2, y equals x plus 2. Put in some of the zeros and the intercepts. We know there's a 0 and negative, so I've labeled this just to help you. This is negative 2. This is positive 2. Let's see. You can use a different color. But once again, you're graphing. So you should be using pencil. Use different colored pencils if you want. Let's see, we have negative 4 and positive 4. This must be labeled. You must label it. What else? We have a y-intercept of 8. Okay, that makes sense. Once again, it's not the best sketch. It's a sketch. That's all it is. If you have graph paper, they'll make it easy for you. And let's see, I think we kind of know what this looks like. I kind of know what this branch, my left branch, kind of looks like. It runs along y equals x2. It passes through this, 0. Let's see, it goes up like that. And then we kind of know it kind of looks something like this. And now we've graphed. Yeah, that's it. Let's see, anything else I want to talk about? 6, 7, 8. No, we're good. Okay.